Thanks for coming. I hope you're enjoying the conference. I am Gabor Szarnyas, and I'm here to talk about the DuckDB system. A little bit about my background. I did a PhD back in Hungary in something called the FTSRG, the Fault Tolerant Systems Research Group, and we focused on critical systems and models of critical systems, which eventually drove me to work on graph databases where you can store these models. Once I finished my PhD, I moved here to Amsterdam. I worked at CWI, the Dutch National Research Center for Computer Science, where Python was invented and Dijkstra's algorithm was invented. And there I worked on graph databases, graph analytics, and database benchmarks. And while I was doing this, in the offices near me, Mark Rasfeld and Hannes Mühleisen invented something called DuckDB, which was an open source project that spun off into a labs company, which is DuckDB Labs, which is where I followed them in 2023, and I worked there as a developer relations advocate. And in this talk, I would like to give you an overview of DuckDB and also some of the internals that will help you understand why it's fast and how you can make your workloads fast in DuckDB. So what is DuckDB? In a sentence, DuckDB is an analytical database management system that's designed to process 100 gigabyte plus datasets on end-user devices such as laptops. And the main observation here is that in the last decade, vendors have been coming out with excellent laptops. You can now go to a store and buy a new laptop with 8, 12, or 16 cores, quite a lot of memory, and a very fast NVMe disk. And this is true for both Apple laptops and laptops by Microsoft, Lenovo, Dell, you name it. These laptops are actually developing faster in terms of speed than cloud machines, and they are definitely better in terms of price-performance ratio. If you browse the cloud prices, the cloud didn't really get much cheaper in the last decade, while laptops have gotten, at the same price, a lot faster. So there is a lot of performance that you can extract from a laptop if you program it correctly. DuckDB's key values are that it's simple to use, it's free to use because it's open source, it's fast, and it's feature-rich. And I think it's best to demo this with a data set. So there is this app in the Netherlands which is about train information, and they release a bunch of very high-quality open data sets. These encode train services, stations, and distances. So I made a little demo with this. And the motivation of the demo is that I've moved here in 2020, and ever since then, everyone I know has been complaining about DNS. Everyone is saying, well, the trains are very expensive and they're getting worse by the year. So I grabbed 5 years of data sets. This is between January 2019 and April 2024. This is about 15 gigabytes of CSV files, and I just started the loading process. The loading command is very simple. We say, create table services from the services CSV file. That's it. And then we return the number of rows that we have just loaded into the system. And you can see that on this very laptop, which is kind of a off-the-shelf MacBook Pro, we loaded 15 gigabytes of CSV files into DuckDB's own format in 11 seconds, so at more than 1 gigabyte per second. And if you want to ask, did the trains get any slower over the years, then we can just say, well, let's extract the year from the service date where the train was running, and let's do an average of the arrival delay, which is encoded in minutes, so I will just convert it to seconds so that it's easier to read. And that's it. It's a couple of lines, and this runs on 115 million rows in 0.2 seconds. So we got a bunch of numbers, and you can kind of see that yeah, the delay is increasing, but it would be nicer to actually visualize this. Now, in many databases, it would mean you have to return it in some sort of a CSV format, read it into pandas, and then do a visualization. Not with DuckDB, though. With DuckDB, we can just route the result of a query into a data frame. Well, it took 0.1 seconds, and then we can use this data frame in a Python code. We can say .plotbar, and there we have it. It's all the complaints actually have some ground truth. Ever since 2020, where trains were running quite on schedule because there were very few of them, the delays have been increasing steadily, and this year is on track to be one of the worst. So what did we just do, or mainly what did we not do in this demo? But first, because DuckDB is simple, we did not have to fiddle with any registration. I'm sure all of you have used cloud services where you have to register an account, or you have to start a server, then you have to configure a client with an IP address, maybe fiddle with a firewall, set up some ports. We didn't have to do any of that. DuckDB just ran with import DuckDB in Python. We also did not enter any credit card details. We didn't have to register for a trial, and we didn't have to do a quota increase, which is one of the worst things when you use the cloud and just want to get your analysis done. What we did do is that we analyzed 15 gigabytes of data in a matter of seconds. Of course, it could be more data. I actually took this data set and boosted it from 5 years to 200 years of railway services, which resulted in 5.4 billion rows of CSV files. And what I noticed is that on this laptop, you can still work with 600 gigabytes of CSV files. Granted, this is nowhere near as brisk as the demo, so you need a medium-length coffee break of 16 minutes to load it. But once you did that, the aggregation is still reasonably snappy. You can wait 22 seconds, and this is still a lot faster than moving all this data to the cloud, setting up a computer, and then waiting for the computation to finish. And the final feature I talked about is being feature-rich. And this means that DuckDB has full SQL support, and it doesn't mean joins, aggregations, and filtering only. We actually do many of the advanced SQL features plus a bunch of SQL extensions. And to show this, I go back to the demo where I have a couple of queries prepared for you. So one of the questions that I had when I started to look at the data set is, which are the busiest stations in the Netherlands? Anyone has a guess? Which is the busiest station? That's a mix of Utrecht and Amsterdam. So let's see the data. We can do a high level of statistics of services per month in the data set. But then SQL has a bit of a difficult thing when it comes to top 3. You can do top 1, but to do top 3, you have to do something called a window function. A window function has this awkward syntax where you go through something using the over keyword. You partition the data based on month, ordering by the number of railway services, and then you rank them using this function. This is something I can never remember from the top of my head, but this is standard SQL. And if we add the rest of the query, which is constructing the month name and then filtering for the summer month, we can indeed confirm that Utrecht Centraal is leading the business competition for every summer month, followed by sometimes Amsterdam Centraal and sometimes by the airport. So this is, again, something that barely took a few milliseconds. And while this is not a particularly nice query, this is standard SQL, and it's portable between SQL systems. Now, a couple of important operations when dealing with data sets and data frames are pivot and unpivot. Pivot means we turn a long table into a wide table. So, for example, this table that we just had, we would like to turn it into a way where we have the train station names as column names, and then the traffic as the column values. And luckily, DuckDB has a very simple syntax for it. We first filter for a long table to get these values, and then we can just say, let's pivot on the station and create the number of services as a summary statistic, and that's it. Again, took minimal time and a very simple, concise syntax. Sometimes we want to unpivot, and for this, I actually used another data set. So we have this data set called the tariffs, which encode the tariffs and the distances between 400 train stations in the Netherlands. You can see that this is kind of a weird table because it encodes a symmetric matrix. So it has NaN values all across the diagonal of the matrix, and then it has the distance between every pair of train stations in the country. Now, this is really unwieldy to work with in SQL. But we can use something called unpivot to turn this into a long table. Now, to do this, in traditional SQL systems, we would have to spell out all the column names, AC, AH, AHP, all to ZTMO, which is really inconvenient. But luckily, DuckDB has something called columns star. And column star, we list all of the column names. We can then exclude the station column, the first column, and the rest is just trivial to write. So once we run this, we have this very convenient table saying from this station, this other station is this many kilometers away. And if we want to find something like the largest distance between two stations, we can just say, well, let's do joins. Let's make sure that it's running from a train station in the Netherlands to another train station in the Netherlands. We break the symmetry with this filter, and we can retrieve Eemshaven to Vlissingen, which means we can take a 426-kilometer train route using just trains in the Netherlands. I actually confirmed this with Google Maps. So if you are a train geek and looking for a weekend trip, this is the longest that you can do without using any bus in the country. So these were a couple of advanced SQL features, but DuckDB has more interesting characteristics that allow this performance and this usability. The first one is that DuckDB is in process. This is quite a fundamental shift because it was very widely acknowledged back in the data warehousing and data analytics world that the client-server architecture is necessary for data analytics. And the reason for this is that the data analytics itself had to run on some big iron. It had to run on a big server that could be in the on-premises cluster of the company or in the cloud, but it had to be something that's a big machine. And there are many problems with this. One is that the big machine is going to be expensive. Two, the software running on the big machine is probably going to come with an expensive license. Someone has to set it up, someone has to operate it, and even once we are done with all those, you have to deal with these arrows in the middle. You have to make sure that your client can connect to the server. The client will then communicate over a slow network and potentially over a slow database protocol. So this is all quite unwieldy. And DuckDB said, well, the laptop on the left shouldn't be just a glorified terminal. It should be something that actually does the data processing. So we took the database and we moved it into the client process that's running on the laptop. And serverless has a bad name as a term because people say, yeah, AWS Lambda is serverless, while there is definitely a server doing some work in the background. Well, DuckDB is truly serverless. We remove the server and there is no more server. But what we do have is we have a single file database format that makes it very easy to work with DuckDB and then stop working, maybe pass your partial work along to a colleague. You can just attach it to an email, upload it to an S3 bucket, and this makes it very convenient to use DuckDB. If you are familiar with other database systems, this quadrant image is very helpful for categorizing DuckDB. The in-process deployment model itself is not really novel. You probably know SQLite is the most deployed database on the world. And SQLite is in process, but it targets a transactional workload where you add a couple of rows, query for a couple of rows, and then maybe delete a couple of rows. But DuckDB is more in line with bulky analytical processing, similarly to data warehouses like Snowflake, Vertica, Teradata, Databricks, and so on. So what is this internal working? How do these data warehouse systems work? Well, it all starts with the storage. The transactional systems, SQLite, MySQL, and Postgres, they use something called a row-based storage. So if we use the railway dataset where we have a date, an ID, a type, and a train station, then a row-based system would group these together, a given date, a given ID, a given type, and a given station, and store those together on disk. And this is great because it allows for easy updates and easy queries for a given row. But the column-based system stores it by column, which means that you can compress really nicely on a data that is of the same type in consequence, and you can store these on disk together physically. And it also allows you to just throw away columns. So if you need to do some statistics based on date and station, which we already did today, then the ID and the type columns do not have to be read from disk. So there are lots of savings to be done there. The next step is the execution. Traditionally, systems did something called a tuple at a time execution. This is very easy on memory because you just have to get one tuple in the memory, process it, and then the next tuple, the next tuple, and then the next tuple. But this is more akin to working like writing a line of program and then changing to your email client, writing another line of program, writing another email. We know this is not the best of office productivity. What's better is to do all the programming and then all your emails. And this is column at a time execution. And this works really well for analytics because you can deal with this one column in one big go. The problem with column at a time is that you can run out of memory. If your columns have 1 billion or more rows, your system is likely to crash. And this is one of the reasons why systems like Pandas often run out of memory. Pandas is column at a time, and you can run out of memory. Now, there must be some better interim Goldilocks approach, and this is called vectorized execution. Vectorized execution means that you process the data in vectors, where the vector is maybe 2048 items, and this allows you to do some level of bulky processing and at the same time not run out of memory. And it's even better than not running out of memory, because as we will see in the next slide, these vectors are selected to the size where they actually fit into the L1 cache of the CPU. So what we see here is 8 rows. They are split into 2 row groups, 1 to 4 and then 5 to 8. And we split them between the CPU threads based on the row group. So we first send these to the 2 CPU threads, and then we start doing the processing based on the vectors. We first process the first pair of vectors, and then we process the second pair of vectors. And because modern CPUs have L1 caches around 32 to 128 kilobytes per core, this 2048 item in the vector and related columns most of the time fit into the L1 cache, which is much, much faster even compared to main memory. Of course, this sounds very neat, and you may ask, why didn't everyone do this before? I mean, this is how you should get the most performance out of your system. But the problem was that this is really difficult to port because you have an Intel CPU with SSC2, you have an Intel Xeon with AVX512, and then you have an ARM CPU, and you would have to manually program all of them, particularly with SIMD, single instruction multiple dataset instructions. And this makes portability really difficult. But luckily, over the last 15 years or so, the main compilers, GCC and Clang, have started to auto-vectorize code. So if you write code in a way where you use tight for loops, there are no branches in the code, and even when there are, they are made out of the for loops, the compiler will be able to create code that is using SIMD instructions, and that will allow you to get the best performance of the CPU while maintaining portability. And of course, things are not as simple as on this slide. Sometimes you have to build some hash tables, do some larger state in memory, but this is the key idea that allows DuckDB to be fast. The other idea that works really well in DuckDB, and it's probably not talked about enough, is zone maps. So DuckDB creates zone maps, also known as min-max indexes, for each column in each row group. And this works really well if the column is ordered or almost completely ordered. For example, you can see that for date, for the first row group, we here created min, max, May 30, and May 31st. And in row group 2, we created 1st of June and 2nd of June. So if someone says, I only want summer month, then DuckDB can immediately just throw away row group 1 because there cannot be a potential match in row group 1. This also works well for IDs, and it doesn't really work for strings. So for the type and the station columns, this doesn't work that well. But in many of the cases, zone maps is all that you need for indexing. So I talked about portability between different architectures, but having auto-vectorization in the code is not sufficient. What you really need is a code base that's written in a single language. We selected C++11 because it has a compiler available on most platforms. But we also had to be very stringent on not using any external dependencies. Dependencies are notoriously difficult to port, and we cannot just rely on some sort of a regex library or an SSH library being on the machine of the user. However, we also cannot rely on completely redeveloping a regex library or SSH for that matter. That's just a recipe for disaster. So we have a bunch of inline dependencies that are part of the code base. We vendor those dependencies into the code base. It's still C++11 in its entirety. And this means that DuckDB is very portable. It doesn't have any dependencies to hold it down. And thanks to this, we have clients for many platforms and many programming languages. We have a Python, R, Node.js, Java, Rust, Go, and many different clients, also a standalone CLI application, and our crown jewel, which is DuckDB in the browser. On the left, you can see it running on a desktop computer, and on the right, you can see it running on a phone. So DuckDB is so portable that in your phone, in your browser, there is a WebAssembly client, and DuckDB runs the web shell in your phone and works reasonably well for medium-sized data sets. So let's talk about ergonomics, because this is something databases have not always excelled in the past. Well, DuckDB supports many formats and protocols. So it can load CSVs, Parquets, and JSONs, as you would expect, but also now the data lake formats like Delta and Iceberg. And it supports the HTTPS protocol, the AWS S3 protocol, and the Azure Blob Storage. And these work in tandem together. So for example, if you do something like a request for a Parquet file that's sitting in an HTTPFS endpoint, then DuckDB will not fetch the entire Parquet file, load it over the wire, and then do the query. Instead, it will read the metadata of the Parquet file. It will say, oh, I only want summer month, and I only want the date, and I only want the station name. And then it will fetch those columns using HTTP range requests, and this can potentially save a lot of traffic. I wrote a blog post about it, and it turns out that if you query for summer month and a couple of columns, it only does about 6% of the dataset size as network traffic, so you can really cut down on transfer costs and egress costs if you're using the cloud. Continuing with the protocols, DuckDB can directly connect to the transactional databases. So we understand that a lot of data is in MySQL, Postgres, and SQLite. And while you can export a CSV file from these systems, it is not the easiest thing to do and to parse it back. It's much easier to just connect directly to these systems and query their tables. And finally, a unique feature of DuckDB is that it integrates with things like the Pandas library, NumPy, and dplyr in R. And we can do this specifically because of the in-process setup of DuckDB. Here's a small example where we import DuckDB and import Pandas. And what we do is that we define something called my_df, which is just a Pandas data frame with 2 numbers. And then we run a DuckDB query. And what's happening here is that DuckDB is querying from, using the SQL from clause, the my_df table. But this table doesn't exist. So DuckDB says, well, let's try to do a replacement. It's called a replacement scan. It's looking around in the Python environment, and then it finds that there is something called my_df, and then it reads that Pandas data frame. And there are a couple of important things here. First, that this read is happening without creating a copy in DuckDB. In the big data world, it's in general a bad idea to copy things between systems because it's just a lot of performance loss for no good reasons. So we do a zero copy access. But DuckDB is parallel. So DuckDB is essentially reading Pandas data frames faster than Pandas itself. And once you're done with the computation, and as you have already seen in the demo, you can just take the result that DuckDB gave and turn it into a Pandas data frame. And we made this integration specifically to make it easier to introduce DuckDB in a Pandas code base. We understand that there are large Pandas code bases. Most of them work perfectly fine. But sometimes there is heavy-hitting operation, and maybe you just want to do that one operation with DuckDB, and that is perfectly good, and that's a valid use case for DuckDB. If you want to use DuckDB, there are now lots of IDEs supporting it. dbeaver is a classic system. There are new systems like QStudio or Harlequin, a terminal user interface. And it works really well in Jupyter notebooks. There is JupySQL support, and you can return tables. You can integrate with Pandas, as you have seen. So this is all very ergonomic. What's the state of DuckDB? Well, June has been a busy month for us. We had this upshot sling at the end of the star diagram in our adoption. So we have about 19K GitHub stars, 30K followers on LinkedIn and Twitter. We have now more than 1 million visits per month and 4 million plus PyPy installs. And at the beginning of the month, we have just released something called Snowduck. This is an homage to the Apple Snow Leopard system, where they released a macOS version with the slogan that the feature of the system, the new features, is that there are no new features. So in Snowduck, we focused on stability. We said this is a DuckDB version where if you create a database, new versions will be backwards compatible with those, and you will be able to read this DuckDB file for the next 5 to 10 years. And to celebrate this, we actually had these big data on your laptop posters scattered across Amsterdam. You can see the very nicely composed picture with the canals, the bike, and the DuckDB poster. DuckDB has an extensive way for extensions. We said that we don't want dependencies, but sometimes you just have to package something that's really heavy hitting, and we don't really want to compromise our core with having big bulky dependencies and having the system swell up to 100 megabyte plus. So we have a powerful extension mechanism where you can register new functions, new types, new data formats, operators, SQL syntax, even memory allocators. And we are heavily dogfooding this. So many of the key features that you see with DuckDB are extensions. This includes HTTPFS, JSON, and Parquet. Many of them are built in, but these are still extensions that you can turn on or off. And what we want to do going forward from version 1.0 is an extension ecosystem where DuckDB is in the middle. It acts as kind of the fabric between different extensions, and you can do something like HTTPFS request over Parquet, and these work in tandem, and these integrate with other DuckDB extensions. One of them may be something for a data format, the other one may be VSS for vector similarity search. So what are the use cases for DuckDB? I have collected a couple of use cases over the past few months, and by far the first one is reducing costs. People are a bit fed up with cloud data warehouses because even though they are ergonomic, they are very scalable, they are extremely expensive. So replacing a proprietary system or even replacing partially and just doing some computations locally will save you a lot of money. And if you replace distributed systems like Apache Spark, DuckDB will save you there on the efficiency front. This is a slide that Hannes also showed in his talk. This is a TPCH experiment on Parquet files, where it's roughly 40 gigabytes of Parquet files and the TPCH workload from query 1 to query 22. And you can see that Spark on 2 machines is completing it in about 8 minutes, and DuckDB is taking 1 minute and 16 seconds. Now, the thing is, you can scale Spark, you can add more and more machines, but because of the overhead that is introduced by running distributedly and all the coordination that those nodes need to be doing, Spark will never catch up with DuckDB. So even though you spend 32 times as much on the costs of the machines, it will still be slower than DuckDB on a single machine of the same type. Of course, I'm not here to tell you that Spark is bad. Sometimes you have 100 terabytes of log files, and there is no way you can deal with those with DuckDB on your laptop. Then we recommend you to keep using Spark, run it on a 100-machine cluster, and usually you can throw away most of the data and save just a bunch of statistics. So maybe you will have a 50 gigabyte summary table. Then you can take that as a Parquet file, put it on your laptop, and do the last steps of the analytics very interactively, very conveniently with DuckDB. There are a bunch of companies now like Evidence, Real Data, and Streamlit, and they take this very idea and they build dashboards on top of DuckDB. And these dashboards run in the browser, so they run DuckDB in the WebAssembly shell. And this is a very snappy, very nice user experience. They call it 120 FPS dashboards because it's very convenient that you click and you get the result immediately. People do local prototyping all the time. There are now libraries that translate between the dialect of Snowflake and Databricks to DuckDB. You can program in your local environment. It's completely free. It's very responsive. And because it's a standard SQL dialect, the portability is reasonably good, even if there is no automated solution. One thing that really drove me to use DuckDB is that it's something that you can use as a building block. So you have a larger system, it's maybe nothing to do with data processing, but there is a step in between where you can use DuckDB. Maybe you have a Parquet file and you need to turn it into a CSV. Or maybe you have to do reading 100 million records and you don't want to use some Java library that does it line by line. Here are two use cases that I did during my academic work with students. And these were Java code bases where we just noticed that you do something in a for loop with some very simple data. We rewrote the whole thing in SQL, ripped out the original Java code, and this led to parallel processing, which is much faster, and also these very satisfying commits where we could just throw away 5,000 lines and replace it with 1,600 lines in DuckDB. The interesting thing about this is that this is totally not a database use case. You would never use Snowflake for this or Vertica for this. But with DuckDB, because it's so portable, it can be used as a building block. And finally, DuckDB can be used in education. It's very easy to install for the students. It's open source. It uses de facto standards. And you don't need to have a DBA who has to be phoned out of bed during the weekend because the students crashed the cluster again. This did happen when I was teaching databases. With DuckDB, there is no server, there is no DBA, no configuration, so this works really well. So what are some limitations of DuckDB? Well, one big limitation is that because it's in process and because it's focused on analytics, we do have transactions, but you cannot do multiple writers. So if you try to connect to the same database instance with multiple writers, it will throw an error. You can, of course, read and write a single database, and you can read the same database from multiple DuckDB clients, but this is a limitation in concurrency control. And the second is that DuckDB is limited to single node execution. DuckDB can scale up, and the cloud has gone a long way in the last couple of years. You can rent machines up to 36 terabytes, although the pricing is a bit of a joke, so I just put that in gray. But you can easily get enough memory and enough CPUs if you want to go back to big iron style processing in the cloud. And one thing that is very good for DuckDB is that you don't have to pay these outrageous prices every hour. You can just store your data in an S3 bucket, or even better, an S3 Express1 bucket, and spin up a computer, run the short burst of workload, save the data back to S3, and then you still get a pretty good bang for your buck. So what's the business model of DuckDB? Well, DuckDB Labs is a company that's based in Amsterdam. And one of our principles is that we are funded by revenue. So we didn't take any venture capital, but we kept the company rather small and kept the growth at a reasonable rate. And we consult and support for DuckDB. So we work with a bunch of companies like Databricks, Fivetran, Real Data, Hugging Face, and so on. And we provide services for them around DuckDB, including premium support. The DuckDB Foundation is a non-profit. The idea of it being here is that even though we do not want to be acquired, it is possible that at some time in the future, big tech company X will just buy DuckDB Labs and close down the source. But the source is actually not owned by DuckDB Labs. The source is with the DuckDB Foundation. The DuckDB Foundation owns the intellectual property, so it cannot be relicensed through the company. The DuckDB Foundation is something you can think of as an insurance policy where the supporters ensure that DuckDB still has maintenance, even if the original project, for some reason, does not continue. And we have companies building on DuckDB. So I mentioned that we do not do multiple writers, and we do not really scale that much. Well, we have a partner company called MotherDuck. They are venture capital funded because they are building a cloud data warehouse, and you cannot really build that based on revenue. And they are based in Seattle with offices also in San Francisco, New York, and here in Amsterdam. And MotherDuck do a cloud version of DuckDB with many interesting ideas, such as hybrid query execution, where part of the query runs on your laptop and the other part runs on the server. So MotherDuck just reached general availability yesterday, so they went to the open market, and we hope it's going to work out really well for them. They have a really nice product with quite interesting ideas and very strong ties to the DuckDB ecosystem. So to sum up, if you think about the spectrum of data processing systems, you have really small data sets like Excel data sets and also pandas on the left, and you have really big 10 terabyte plus data sets on the right where Spark makes perfect sense. But we believe that there is this middle ground between, say, 10 gigabytes to 1 terabyte when Pandas is not scalable enough and Spark is a bit too much to set up, and DuckDB fits really nicely into this gap. And we are really proud that DuckDB is an old school system in the sense that we don't do business software license. We have a very permissive MIT license. We are very portable, like the good old Unix tools. We build on open standards. Everything works offline. Even the documentation is something that you can just grab. Here's a PDF, and then you can work on the train without being permanently connected to some annoying endpoint in the cloud. We do not track you. We do not use cookies. We don't have telemetry, and so on. So if you found this interesting, then head to duckdb.org and give it a try, and also stay in touch. Thank you so much.